Okay, hi everyone. And my pleasure today to introduce, if you haven't met Lydia yet, this is Dr. Lydia Fang. And so I got to know Lydia. She was working in David Binge's lab, who's a very famous sleep researcher at the University of Pennsylvania. She was doing her PhD there, finishing it. She started in China and went to Penn for 2011, 2015 or so. She was in the Department of Neurology and psychiatry there, where then she started doing some additional research there and got her hands into all sorts of neat things that actually some of you might be interested in, things like nicotine and cocaine, marijuana, also diet and how these things relate to sleep, and done some really nice neuroimaging work there, which is what really caught my attention. And she came to my lab at Western when I was there from about 2015-17ish, and at Western, this is the data that she's going to be presenting today. So yeah, and that was in collaboration with Dr. Adrian Owen, the consciousness guru there, and Lydia came to really get going our program of EEG-fMRI sleep research, and so she mastered these techniques very quickly and collected a humongous sample of over 30 people sleeping in the scanner, which is, as far as we know, the biggest data set of its kind in the world. So we're actively mining this right now, and she's going to show you what came of that so far. So my pleasure to introduce Lydia.
Thank you, sir. Okay, so I'm very glad to be here today sharing our study and the results with you, and which is from the EEG-fMRI study. Yeah, like Stuart said, this is my postdoc project at Western, and this is supervised by Dr. Adrian Owen and Dr. Zhuo. Okay, so today's talk will include some research background and some technical methods and some main findings from our study. Okay, it's a common sense that generally we spend 1/3 of our life sleeping. So for our short life, this is really a huge amount of time. So before all those sleep research came out, people used to believe when we go to sleep, our bodies and our brains actually go into a shutdown mode. But for the evolutionary aspect, there must be some reason why humans need so many sleep. So from 1950s, sleep research increased in lots of fields like the biological science, cognitive psychology, neuroscience, and other areas. So according to the previous sleep research, briefly, sleep actually is a highly organized and active brain state with decreased awareness of the external ongoing events. So sleep offers our brain an opportunity to rework and reconnect the information we collect throughout the day. So from that we can see sleep is not only important to our health, it's also important to our cognitive performance. Okay, now let's see what is sleep going on. So it has been identified that typically the sleep goes through 5 stages. And from stage 1 to stage 4, which we call it non-REM sleep. It means because during the 4 stages, there's no eye movement. And then there's another unique sleep stage called REM sleep, because there's the eye movement is very rapid. So typically during one night, the sleep goes like a cycle. So from stage 1 to REM, and then go back to stage 1. And usually one health individual will go 4 or 5 cycles during one night. And now let's take a look at the brain waves across the different sleep stages. So when we are awake, the brain waves are almost a beta wave and alpha wave. The beta wave is more associated with the day-to-day awake, which involved lots of mental activities, including the cognition, sensory movement. And the other the other waves is the alpha wave. It's more associated with the relaxed or the still awake. And during the wake, we can see the beta and the alpha waves are very high frequency and low amplitude. And then when we go to the sleep 1 sleep, the brain waves are most the theta waves. And we can see the frequency is relatively lower and the amplitude is relatively higher. And then we go to stage 2 sleep. And during this stage, the theta waves continues, but there's other two very unique brain activity, which is sleep spindle and the K complex. And these two features is very unique for the stage 2 sleep. And then we go to stage 3, which we call it slow wave sleep, and it's consistent of the delta activity. And here we can see the brain waves are the frequency is very slow and the amplitude is very high. So this sleep 1 to 3 is the non-REM sleep. And then the other is the REM sleep. So in REM sleep, the brain waves is very similar with the wake condition. It's very high frequency and low amplitude. It's a combination of the alpha and the beta. So in our study, we mainly focus on the sleep spindles because there's a previous EEG study have found that sleep spindle is highly associated with the human intelligent abilities. And actually, sleep spindle is the only neural oscillation has been found to related to humans' cognitive performance. So here maybe someone want to ask why you think there should be a relationship. Is this finding is just some random correlation? Here is the why. So based on the previous EEG studies, it has been identified that sleep spindle is very consistent for any individual from night to night. So for this reason, the sleep spindles have been considered can serve as electrophysiological fingerprint. But the significance of this function of the spindle has not been well understood. But as we know, the other trait-like factor is humans' intelligent ability. It's also very stable across individual. So because these both of the two factors are very trait-like, so there has been some hypothesis they should have some relationship. And actually, previous EEG evidence have already revealed the inter-individual difference in spindle characteristics are related to capacity for reasoning. And here I want to show you some example of the EEG studies. So this study is from Dr. Fogel. They found the number of the sleep spindles is positively correlated with the humans' performance IQ, but it's not correlated with the verbal IQ. The other two studies have also found that the fast spindles activity is correlated with people's humans' reasoning ability, which used from the Raven tests. And also there are some other studies also found the similar results, but I didn't list here. So based on all those EEG studies, it's clear that the sleep spindle and the humans' reasoning ability is highly correlated. But as we know, the sleep spindle is not only related to the cognitive abilities. It's also sleep spindles can also maintain our sleep. For example, it can protect our sleep from the outside stimuli and the outside events. And also, there are some studies have found that there's circadian time can influence the sleep spindles. Means if as we know, some people are morning people and some people are evening type. So this different type of the circadian chronotype is also influencing the sleep spindles. So here's we raise a question: is this relationship between the spindle and the reasoning ability direct or mediated by the other factors like the sleep quality or circadian time? So this is our previous EEG study. We want to examine this relationship is direct or not. In order to examine this question, we used the mediation model to review this question. So first, we use the multiple regression to replicate the relationship between the spindle and the reasoning ability. And then we want to find out if these two mediators, sleep quality and the circadian chronotype, would influence or mediate this relationship. And take the sleep quality as an example. First, we have to determine if there's a significant relationship between spindles and the sleep quality. If there is, it means sleep quality has the possibility to influence the relationship between spindles and the reasoning. And then we have to determine if the sleep quality has a significant relationship with the IQ scores. If both correlations are significant, it means the sleep quality has some mediation effect, and then we have to do a third step to determine the mediation effect is partial or fully. So we have done the same test for the circadian. Okay, here is a brief instruction of the mediation model. And here I want to spend a few minutes to talk about the cognitive ability test we used. Here we used the Cambridge Brain Science test, which is developed by Dr. Aiton. And here's the CBS is web-based test, so it's very easy for administration, and the subjects can finish the test online at home. So as the first, it's terrible. It's a mess. You cannot get any information from this picture. But eventually, we have to get this very nice and clean EEG data. Seems it's impossible, but we have to do many corrections and analysis to get it. Okay, now there's two noise. First is the gradient artifact from MRI scanner. So here are some tips. First is what sequence you have selected. So we usually the synchronized and time-stable MRI sequence is the ideal. So as we know now, the standard both EEG should be the suitable sequence for EEG-fMRI study. So like the store has said before, so the DPI sequence is not very good for the EEG-fMRI study because the sequence is too fast and the equipment will move a lot. In the scanner. And the second is you have to choose the TR optimal TR parameters, and including the number of the slices. And here's just some very detailed stuff. I will skip this slide. Maybe we can talk later if you're interested. And here is this picture is the picture after we did the artifact correction of the gradient artifact. And here it seems it's more clean. It's cleaner than before, but this is not the final one. So here from this picture, it seems it's very clean and it's very nice, but this is not the ideal EEG. So here we can still see all these peaks. Where is it from? Okay, it's from our the heart rate. Okay, it's the heart rate influence all these EEG waves. So it seems very clean, but there's a big noise here. So we still have to correct that noise. Here's also some tips for reduce the cardiographic artifact. So first, for example, after we put the subjects into the scanner, we usually shift the 40 millimeters off from the ISO center. By this, we can reduce the BCG artifact by up to 40%. And also for the BP cap, the EEG cap, they had a single EEG electrodes from cap to the back, but the recording quality is not very good. It's very poor. So we applied three additional pairs of the electrodes under this area to make sure we can get very good EEG signal, and then we can do the correction afterwards. Okay, this picture is a comparison of the BCG active before and after the correction. So we can see this red line, the peak, is the BCG before the correction. The green line is the BCG after the correction. It's almost overlap with zero. There's just only teeny tiny, lower than 1 microwave there. So it means our BCG correction is very good and it's adequate for our study. Okay, so this is the first EEG picture we get from lesson, and finally we got this. So it's very nice, and you can even see some the spindles, key complex, and the delta. So after all these corrections and the pre-processings, we got our clean EEG data. Okay, now we have good fMRI data and we have clean EEG data. Then we can go back to our research question. So from this data set, currently we have planned 3 studies. So first study is about the brain activation time locked to spindles associated with cognitive abilities. So basically for this study, first we want to replicate the brain activations to spindles like the previous studies. And second, we want to explore examine the relationship between this activation and the cognitive abilities. The second study is the brain functional connectivity time locked to spindles associated with the cognitive abilities. So first study is only about the
coffee shop at the main entrance is now open, but the chance to there. The cafe available and offering experimental bar. Coffee shop is now open.
Coffee shop. So the first study is about the brain activations only, but as we know now, more and more research argues that the brain is working at networks. So in the second study, we want from the network aspect to see how brain communications related to the cognitive scores. And the third study. So for the study 1 and study 2, we only focus on the spindle, but there's so many specific features. It's not only spindle. So in the study 3, we want to examine the brain activation modulated by the other features, like all the brain waves I have mentioned in the first slide, like the alpha, beta, or the sigma powers. How these features modulate the brain activations and how those brain activations associated with the cognitive abilities. Okay, here's the first study. It's a brain activation time locked to spindles associated with the CBS scores. So this is the EEG and the behavior scores relationship. So we replicate the positive correlation between the reasoning ability and the spindle amplitude, which is consistent with our previous study. And the most exciting part is the neuroimaging results. So for this figures is showing the brain activation time locked to spindle.
Dr. Khan.
Yeah, and from here we can see it's very consistent with the previous 2 EEG-fMRI study. We also found the frontal cortex, the thalamus, the putamen, and the cerebellum cortex. It's activated during the sleep spindles. And then we used the multiple regression whole brain analysis to find out which regions activate during the sleep spindles is significantly correlated with the CBS scores, including the reasoning scores, the verbal and the short-term memory. And here we can see all these regions is significantly correlated with the reasoning scores. And here we can see this region seems like a subset region of the spindle activation, including the frontal, the thalamus, the pituitary, and the cerebellum. To make this relationship more clear, I also run our analysis, and we can see the significant correlation trend of the patterns for the three main regions: the thalamus, frontal, and the pituitary. And here I want to mention that in this model we also included the verbal and the short-term memory into the model, but we didn't find any significant correlation. So it's very consistent with the previous EEG studies, and it provides further evidence to this relationship between spindle and rhythm. And so we can see from the figure A and figure B, it seems there's a good overlap. And to confirm this overlap, we conducted the conjunction analysis to confirm all these overlap regions. We can see the yellow regions. All these yellow regions is the overlap between the figure B and the figure A. So we can confirm that the frontal thalamus, pituitary, and some of the cerebellum it's activated during the spindle events, and it's also related to the reasoning. And like I said a few minutes later, before, there's already some studies have revealed that all these regions is also involved in the reasoning related task. So for this study, we provided very direct evidence to support this relationship. So from our study 1, first we replicated the positive correlation between spindles and the reasoning, but there's no relationship between spindles and verbal or short-term memory. And also we replicated the brain activations time-locked spindles in thalamus, bilateral pituitary, the frontal cortex, and some cerebellum. And then the other findings, the reasoning ability, but not the short memory or verbal, were correlated with the spindle-related activations in the subset of these regions. Okay, now let's go to the study 2. Like I said before, so now besides the brain regions separately, the brain actually is communicated together across the different regions. So it will make more sense to examine how the brain communications correlated with the reasoning scores during the spindle events. So here, I guess everyone is very familiar with these figures. It's from a resting study, and it revealed some very important networks in human being, like the default motor network, and the executive control and the silence network, attention, auditory, and sensory motor, and visual. And every network is in response to the different kind of the human combination and the mental activity. And it has been a long time that the study has revealed that spindles actually is closely related to the neuron communication between the cortex and the thalamus. But this finding is only at the cellular level. There's no neuroimaging evidence to support this communication is related to the spindle generation. So that's why we want to do our second study. So we want to find out what is the brain functional connectivity during the spindle events, and we applied the PPI analysis using SPM. First, we selected 4 important states based on our previous study and also the other literature about the 6 spindles. First is the thalamus, ACC, pituitary, and the PCC. And now let's see the results of the functional connectivity. So we use the seed-based to run PPI. First, for the thalamus, we found that during the sleep spindles, the thalamus is highly correlated, connected to the frontal, to the cortex region. And this is the ACC. When we use ACC as a seed, we found during the sleep spindles, this thalamus and the bilateral putamen is highly connected with ACC during the spindle events. And for putamen, we also found some thalamus and the cortex connected with putamen during the spindles. So for all these three figures, we can see there's a clear network from the thalamus to from the subcortex to the cortex, the ganglia and the thalamus and the cortical. This pathway actually is very close to spindle events, and but the previous study is separate, is examining this activation separately. But here we found actually the three regions, they work as a network to support spindle generation. And also we chose the PCC as a seed because PCC is the very main hub of the default mode network. And the default mode network it has been identified as it's stronger during the sleep stage than the regular resting state. So here we found very clear default mode network pattern during the sleep spindles. So this finding is even more interesting because, as I know, there is some literature has reported this default mode network across the sleep stages. There might be some difference in stage 1, in all the stage 2. They may have some difference of they have some changes of the default mode network. But here we replicate the default mode network during the sleep spindles. So it might provide more evidence to support the default mode network activation during the sleep. Here we also conducted the medical regression to find out the relationship between the CBS scores and the functional connectivity during the sleep spindles. And here we found two significant relationships. First is the reasoning score is related to the ACC and the putamen connectivity during the sleep spindles. And the other correlation is we found the reasoning scores is related to the FC between thalamus and the middle to posterior cortex. So these two results is consistent with some previous studies that the ACC and the putamen, they are very close to close to humans' higher order cognition functions like the reasoning and the planning and the monitoring. And the other is the thalamus and the cortex is very related to the spindle generation and also related to the reasoning-related task. So based on all those research, we believe our study from the functional connectivity aspect providing more evidence to support the spindle relationship, the relationship between spindle and the cognitive scores. And here also we included the verbal and the short-term memory in the model, but there is no correlation with that, with the verbal and the short-term memory. So it's supporting our previous findings. There's a unique relationship between spindles and the reasoning ability. Okay, here's our study 3, which has not finished yet. So today I won't have results, but I want to tell you what we want to do in study 3. So as I said before, there's so many brain activities across different sleep stages. So all the previous studies we have done is focused on the sleep spindle. but there's still other features like K complex or the delta activities. And the most important is the REM sleep. We got 8 subjects have REM sleep. Maybe it's not a very large sample size, but still it's a large sample size for the EEG-fMRI sleep recording. So we will definitely examine the REM sleep brain agitation and the relationship between the REM sleep and the cognitive abilities. Yep. And okay, that's all the results from our study. And here I want to thank Dr. Fogel and Dr. Agent Owen's support on this project, and also Laura's hard work on all the EEG data, and all the grants support our study and our West team. Yeah. Thank you. Any questions?
Yeah, very interesting. It's so intricate, and so it's amazing you're able to capture all this data. It's certainly not easy. So congratulations on that one.
Thank you.
The question I had is that if you suspect a relationship between the spindles and cognitive functioning, are you able to, if you wanted to, interrupt spindles selectively or disrupt sleep when spindles are happening? Does it have consequences on memory functioning after?
Yeah, that's really interesting question, because in the EEG-fMRI, in the fMRI scanner, it's very hard to get the subject's sleep. But for some, it can be done during the EEG studies. So that's what kind of similar like the EEG study I have mentioned very first. So because spindles is also maintaining or protecting our sleep. It can maintain your sleep quality. And then there are some relationships that good sleep quality may support the cognitive abilities. But as our study seems there's no mediation effect on sleep quality. But I don't know whether I understand your question right. So actually you want to say
so I'm wondering, like if outside the scanner, people are sleeping and you can monitoring their sleep and you see the spindles starting to happen.
Okay.
If you were to interrupt that, interrupt the sleep at that point in time specifically, as compared to other stages of the sleep, would you selectively see alterations in cognition?
It might be, and it depends on which state of sleep you interrupt. Yeah, because it depends the first part of the night or the later part of the night. It might be have difference, but I think it depends on which part of the sleep you interrupt, and the alteration of the cognitive ability might be different. Yeah, because here what we have shown is the sleep spindle generation is kind of supporting the cognitive scores. So that's possible. I don't know whether I answered.
There's a neat study in schizophrenics where schizophrenia spindles are lower. They have smaller spindles, fewer of them. They're kind of malformed. And they also have very specific cognitive deficits, memory deficits that are actually related to sleep. And so one study is just the other way. So people try to enhance or boost the system. So they administered benzodiazepines, which have a big boosting effect on spindles. And they actually managed in the schizophrenic patients to restore the memory deficits that were related to sleep. So there seems to be perhaps some sort of adaptation there.
So, Lydia, thank you so much. I mean, as somebody who's been doing EEG-fMRI, I'm starting to get it done. This is insane, and you have to be so applauded. My question is kind of basic because I don't know much about sleep spindles. So you have really focused on, you focused on amplitude in terms of your correlation. So I guess how important is amplitude versus number in terms of these relations? bigger spindle better, as your particular relations show, but then Stuart's show, I guess quantity is also important. So I was kind of wondering, is that kind of consistent with that?
Okay. Yep. Thank you for your question. Actually, it's very. Yeah, I expect that question. Actually, we were not focusing on amplitude. So basically, previous EEG studies, there's also always some different correlation with the spindle activities and the cognitive abilities. So that's why we usually see spindle activity, not the specific spindle amplitude or spindle numbers. Because some studies, they found the correlation between the spindle numbers and the scores and all the spindle density and the scores. And someone found the amplitude. And also there's some study combine the amplitude and the duration, like the spindle size. So yeah, it's not specific to the amplitude. It's always here or there. So that's why we usually see spindle activity.
Yeah, maybe I missed it early on, but so when you do the EEG-fMRI and you want to say how do you define during fMRI when the spindles are happening? Because the spindles happen in millisecond time frame and the TRs every 2 seconds or something.
Yes, usually the spindle duration is up to 3 seconds, and so your question is about how to.
So if a spindle happens at any point during a TR, you call it a spindle positive TR or something.
Right. So
otherwise, it's spindle negative, and that's it.
No, you just convert the time to TR. They're totally synchronized recordings.
Right. So we can extract the onset of the spindles, and because it's precisely synchronized with the MRI recording, so we can match the spindle onset to the MI volumes, the brain volumes. So like an event relate, every spindle is your event, and the event has the onset of the.
But then so the recordings lock to the spindle onset.
So maybe it's a methodological question, right? Cliff, are you kind of modeling it as almost an event design, and that's how you cross?
Right.
So every spindle is basically marked as an event, and so it's
just
an
like
event-related design
related.
in theory.
Mm-hmm.
That's kind of self-generated, I guess.
But okay, so do you tend to have them they go back to back, so you get blocks at the end of spindle positive time, or they're just sporadic, really here and there?
Not block. It's totally even related. So we extract every single onset of each spindles and then go to the first level GLM and using the event.
But do they tend to cluster the spindles, or not necessarily?
You need to
in time,
as a group.
Back to back, or do they happen very sporadic?
It's not block. It's just I think it's a spread. So every spindle is an event, and every event has the matched MI volume, and we got the first level contrast map using the spindle and all the other default constant to get the contrast map of the spindle event. Have I answered that question?
Do the spindles occur, and again, because I don't know anything about sleep, is it typical that you will get a spindle, 2 seconds break, another spindle, 2 seconds break, another spindle, 2 seconds break, or is it kind of spindle, 5 minutes go by, spindle? What is that, or does it look totally different for everybody, and so that is an impossible question to answer?
Okay, that will be a large inter-individual difference of the spindles, like the density. That's what the density, the duration. The duration is all very different across subjects. So, for some people, the spindle is very one by one. It's very next to each other.
Mm-hmm.
But for some some other people, if the density is not that high, then it might be spindle and you have to wait.
Anyway, what I was going at is, so just does that influence how we measure connectivity? If connectivity during spindles, we only have each spindle time period if you measure.
The connectivity we apply to the PPI analysis. It's based on the task. It's based on the event-related design.
It's not based on sleep.
Right.
Oh, okay.
And there's space enough to be able to do this sort of thing. And actually, it's pretty fortuitous that if they were really close together,
it would suck for your model, right?
Yeah, your model would be
It's kind of random. That's actually perfect for an event.
It's relatively random, and there's enough spacing. They tend to be about 30 seconds or more apart, on average. But there's lots of variability in it too.
So I know that the time resolutions are obviously going to be quite different between the image capture and the time frame of the spindle itself. But I'm wondering, are you able to differentiate so if the trigger is the onset spindle, so you're going forwards in time, if you were to go backwards in time, would you see activation? Because what I'm trying to get to is that what follows what?
No, you said a little bit bad.
Because is it like the activation goes up and then the spindle happens? Because I'm thinking about cause and effect.
Yeah.
You mean maybe there's a time difference between the actual MRI volume and the spindle onset?
Yes, I'm wondering whether if this was your spindle onset, if you were to look at a few seconds time before the spindle actually happened, looking backwards, would there have been an activation in that region of the brain? So that might give you an idea of the causation, whether there's an activation first, then you see the spindle. Because it's always locked with the spindle, which is what you want, right? I'm just wondering whether you can make a cause and effect connection by looking backwards rather than forwards in time.
That's really good.
So, the spindles they're kind of a complex of other events as well. So they're actually coordinated by these very, very slow oscillations you can't even see. And they coordinate this activity, and that ramps up quite slowly before the spindle. I mean, you're here, you know this part. But yeah, there's this slow oscillation that coordinates spindles and actually hippocampal activity and other features of sleep. And that happens before the spindle happens. So there's some sort of pre-brain activity that is going on. But yeah, our model would be totally blind to that.
So it's really a good question. So what I can say is just when we modulate the spindle activation, we use the actual spindle duration into the model.
Yeah.
So that might reduce some concerns, but like what you said, it's please.
Oh, sorry.
I think there's still another question.
Okay. I was just wondering if you guys are doing that, the positioning where you look back at what you want to do.
I triple check that.
Okay, now let's look. Okay, now we're humans. Yeah, that's awesome. Go ahead.
So I actually volunteered for one of those studies at Western, but quickly got screened out when they saw my sleep schedule. But I got a couple questions.
Did you have spindles or not?
Well, my first question is related to the previous questions. What is the spindle duration? How long does that last?
So it's up to 3 seconds.
Up to 3 seconds?
Yep.
Okay. Because over the course of your scan, you're acquiring different slices for, say you have a 3-second TR in your fMRI. At different time points, throughout that 3 seconds, you're getting different slices. So the different parts of you might be looking at connectivity at different slices at different times, I guess. Not much you can really do about that too much, other than like taking the raw data, filtering it from there. But I guess something to keep in mind. I'm assuming you don't do anything like that now, right?
We didn't. I guess what you said is what kind of the dynamic connect along with the time. But now what we have done is not that we have done just the traditional PTI, the functional connectivity. That's a very good point. We can keep that in mind. Thank you.
My second question, I'm assuming it's about the artifact you're seeing with when you're running the fMRI. I'm assuming that's from the changes in the gradients, right? It's not just from the amplitude. If the gradient's on, do you see the artifact, or does it have to be a change in gradients?
There's like a perturbation. You can see like waves can be a little bit malformed just from the static field.
Yeah.
The artifact is from the gradient.
So it's mostly from the eddy currents from the changing gradient. So my question, I guess, would be, you can actually design your study to have slower forming gradients so that the rise time of the gradients is as slow as possible, as compared to if you had it fast, you might be able to get a quicker echo time or a better repetition time. So do you design your study around minimizing that artifact, or is it that easy to get rid of that you don't really care too much about it?
Actually, I guess there's one slide to list the details, but I didn't talk about too much. Yeah, actually, we optimize the MI parameters. Like we choose the TRS 2.16 second, and the number of slides is 40. So for these parameters, we can get the noise, the gradient noise to just influence for the higher frequency, like the 18 something. But our interest frequency is below 16. It's between 11 and 16. So we actually optimize the parameters to make sure the gradient effect is beyond our interest frequency.
Okay. And do you do that by changing the rise time? Like there's parameters you can change. There's fast, normal, and whisper, I guess.
It's more about the timing than the shape of it.
Okay.
Yeah. Because the trick, the way that it works, is the gradient.
You mean
like how the gradient looks on just the mess, though, not the actual. The gradient artifact is like orders of magnitude bigger than the EEG signal itself.
Yeah.
It could be like 10,000 microvolts, whereas we're looking at something that's 100 microvolts. And the only reason you're able to remove all that is that you measure it really, really well. You measure the artifact by having a crazy high sampling rate, so it's at 5,000 samples a second, and we have the amplifiers that are really specially constructed to measure it. And then because you measure this thing, and the timing is very precise, and you know to like the microsecond the timing of when the TR happens, then you can use it by averaging and subtracting from the EEG. And if everything's precise and because the gradient artifact is very predictable in terms of the artifact is the same every time, that you can subtract it out. So it's not too much about like rise and fall and things like that, although it'll influence how the artifact looks. It wouldn't necessarily change whether you can remove it or not, or optimize that. The optimization is in these sorts of parameters that he's talking about, and that has to do with timing. Because there's always going to be residual, and you want that residual artifact to be out of your frequencies that you're interested in studying.
Yeah. Okay. So I would think that you could minimize the residual if you had like a whisper setting, so like a minimum rise time, because then it would be less eddy currents to begin with.
You could probably minimize the size of it, but it's already so much bigger that the size is sort of like it's so beyond anything. It's all timing. Yeah. Okay. That's what it comes down to, and having things be one another over time, you get this sort of like shifting that happens. And but if you calculate things correctly and everything divides into everything evenly, then you have this very time-stable artifact that appears there, and then there's no jitter or anything of the artifact, and you can take it out more effectively.
Sure.
So the data collection, so are you still collecting in London, or are you only collecting from here now?
No,
Here. So are you able to pool the data?
possible. In fact, we also have another data set from Montreal that has the same parameters. They're different machines, but
Yeah.
we would be the first people to use different machines. But a lot more things are common between the three sites than different. So I think there would be the possibility of putting together. And Yorick, actually, like we are collaborating with him now, and the hope is that we would be able to pool the data. We're doing it separately for now, but yeah, it could be very advantageous to combine all of these. And in fact, what I would like to do is to be able to continue this on and use these data as a control data set for to look at other things here, like aging or other populations, clinical